Okay, this is the second chunk of worksheet 12.7, which is for response number 2. You should have tried these before watching this video. You should be getting to the point where you're starting to see these kinds of problems multiple times and starting to get a good idea of how to do these. So let's see if I can make this brighter. I don't know if that works. So anyways, okay, so we did problems, I think, with 5, 1, and 2 before, and these are the last half of the problems. So let's take a look at this. The rate of fuel consumption in gallons per minute recorded during airplane flight is given by a twice differential strictly increasing. If they say something like that, it might be something you need to know. Function R, time, the graph of R, and table selected values of RT for the time interval 0 to 90, 0 to 90, 0 to 90 here. So they've given you a graph and a table of the same information. Okay. It says, now when you have tables and no equation, they haven't given you an equation for anything, you should probably assume that you're going to use some estimation techniques like Riemann sums, trapezoidal approximations to find an integral, slope between neighboring points to find, the slope of a secant line, either the average slope, average derivative, or just to estimate the slope or derivative at a certain point nearby. So part A says to use the data in the table to find an approximation for R prime 45. Show the computations lead to your answer. Indicate units of measure. You should be putting units for sure anyways. So R prime 45 is going to be approximately, so now 45 is right here. So let's use the two closest points to the point we want and do a rise of run. So it's good to show the setup. So R prime is the slope of R. So it should be change in R. R 55 minus R 40 over 55 minus 40. I would show this. This is the setup. Now, the rest of it, we're just, I messed up. 50 to 40. So plug the times in. Now, the y values, the r values are 55 and 40 over 50 and 40. Show the work, label it, show the setup. Be careful. You could leave it unreduced if you want. You could leave it 15 over 10 if you want, or you could take a 5 out of the top and bottom. Just be careful. Now, the units are going to be whatever R is, and if you look at this, it's gallons per minute. Okay, but that's just R. R is gallons per minute. The thing on the bottom is the derivative of R, so it's another time. So it's gallons per minute squared, or gallons per minute per minute. So this is an approximation of R prime 45. Don't refer to it as the average R prime value, even though it is the average between 40 and 50. The work looks the same, but they didn't ask you for that. So the point breakdown is 2, 2, 2, and 3 to add up to 9. This was 1 point, I think maybe just for like the setup, and 1 point for the answer with units. If you didn't put the units, you put the wrong units, you lose a point. So that's something a lot of you guys lost on the last practice test, was just units, not putting them and putting the wrong ones. Look at the information they give you to figure out the units. Look at the work and say, okay, what are the units of this? What are the units of this? That's going to be the units of my answer. B, the rate of fuel consumption is increasing. The rate is increasing fastest at t equals 45. What is the value of R double prime 45? Explain your reasoning. R double prime. Now, that's the second derivative. That's the derivative. Okay, it says the rate, which is R, right, is increasing. That means the derivative of the rate. Okay, fastest. So at time t equals 45. Now, if you look at the picture, that's around there, and it kind of looks like that's possibly the steepest part of the curve. So that kind of makes sense. That the derivative of r is already a rate. So this is r prime. This is like r prime max. Okay. So what's it say to do? It says to find r prime 40, r double prime 45, and what we're going to say is if r prime is a max, then this is going to happen at critical points of the derivative, critical points where the derivative of r prime is 0 or undefined. So it's either going to be 0 or undefined. Can it be undefined? Well, it says it's twice differentiable, which means its second derivative exists everywhere, which means its second derivative can never be undefined. So that means that r double prime has to equal 0. Okay? Now, this is definitely a challenging problem. It's only worth 2 points. And you need to explain it since r prime 45 is a relative maximum, and r double prime 45 cannot be undefined. So we got to rule that out because critically it could be undefined or 0. Why can't it be undefined? Since r is twice differentiable. Okay. And twice differentiable, just to make you understand, that means that the second derivative exists. It is always defined. It exists. Anyways, you don't need that. That's more of a note to you. And then that's it. So that's 2 points and 1 point for saying it's 0 and 1 point for your reasoning. So that was definitely a challenging problem, but on the AP test, don't get hung up on something like that. I don't think you're going to need that to be able to do necessarily the other problems. So if you're kind of puzzled, don't spend a whole lot of time on it. Skip. It's only worth 2 points. There's plenty of other points. You don't want to run out of time and not do problems that you totally could have done because you spent too much time on a problem that you might end up getting wrong anyways. So be strategic. C says approximate the value of the integral of 0 to 90 of RT using a left Riemann sum, 5 subintervals indicated by the data in the table. All right. 0 to 90 RT dt is approximately, now I'm going to draw a picture, and it says we're using 5 subintervals. We're going 0 to 90. So 1, 2, 3, 4, 5. I like to just draw these rectangles. So 0, 30, 40, 50, 70, 90. And I'm not trying to make this accurate at all. 20, 30, 40, 55, 65, and 70. And we're using a left Riemann sum, so it means we're using the left side. So I might just emphasize that, which means we're not going to use this. The bases, which it might be worth writing them down, are changing. They're not all the same. Okay, now you want to show this picture is great and all. That's not gonna get you probably any credit. So anything you write in here, don't expect to get credit for it. Now you need to show the work for finding the areas of rectangle, but not in this picture. So you need to show over here 30 times 20 plus 10 times 30 plus 10 times 40 plus 20 times 55 plus 20 times 65. Like, you should write this. And don't just start. This is one of the other things I was complaining about on your practice test. I don't know if anyone, if you've seen it yet. people just start writing that. I'm like, well, what is that? Oh, this is the integral of RT from 0 to 90, and it's an approximation. Like, label your work. Don't just have random numbers and things popping up. Like, lead with, what is this calculation? Now, this is going to be 600, 300, 400, 110, 110 with an extra zero, 120, 130 with an extra zero. And then we don't have a calculator, so we just got to add these up however you want. 0, 0, 10, 17, carry the 1. So this is going to be the integral of 0 to 90 RT. I'm just going to rewrite it. DT is approximately 3,700. Now, what are the units? Well, R is gallons per minute, and DT is minutes because it's time. So this should be gallons of fuel. Right? Put the units. What else do they ask? Is this numerical approximation less than the value? Explain your reasoning. So they're kind of asking, is this an underestimate? Is this an underestimate or an overestimate? Now, just based off of our very simple picture, it might give you kind of a rough idea. I made them keep going up, and it looks like an underestimate, right? Because it's a left Riemann sum. Now, is it because it's increasing, or is it because of concavity? So whether it's concave down or concave up, left Riemann sums, if they're under an increasing curve, they're going to be underneath it. If the left ones are under a decreasing curve, there's going to be an overestimate. So this has to do with increasing decreases. So we have to say that, let's see, this numerical approximation is, well, I mean, I think we could say it's an underestimate, is less than the value of 0 to 90 RT dt. Why? Since we are using a left Riemann sum, and that's not enough, with now, how do we know that this is actually increasing for sure? Like from a table, just because it looks like it's going up doesn't mean that it's really going up in between. It could be going up and down and doing all kinds of crazy stuff. So just because the values are going up on the table isn't enough to know that it's going up for sure all the time. But they told you this fact right here. They said it's strictly increasing. This thing, they had to tell you that. Otherwise, you couldn't answer this question. And so you should refer to that. With since we are using left Riemann sum, and RT is strictly increasing. So you got to say it's left Riemann sum, and you got to mention that it's increasing, and you got to know that it is less than. So often with approximation techniques, you might be asked if your approximations are over or under the actual value. Part D says, from 0 to 90, explain the meaning of the integral of 0 to BRT dt in terms of fuel consumption for the plane. What does that mean? Well, this is a derivative. R is a rate, right, of fuel per hour. And we just calculated it and gives you gallons. So generally, if you're integrating a rate or derivative, the integral of it is the total change in fuel. And in this case, you might say it's the amount of fuel used. Now it says, we got to make sure, I'd put units in here. Total amount, the total change in fuel, or we could say amount of fuel consumed is a little better interpretation in the context of this problem. In gallons from time t equals 0 to t equals b minutes. Okay, if you don't mention the time, you don't put the units on the time, you don't put the units on the thing, like you could lose your points for it. Okay, so you should start getting used to this. A lot of times we integrate derivatives or rates and they give us the total change. It's like fundamental theorem of calculus, right? If you integrate derivative, you get the original function and you plug limits in, you get the change in the function. Now, what else they ask us? They say explain the meaning of 1 over b 0 to b rt dt. So this looks very similar, but it has a 1 over b in front. What and by the way, it says indicate units of measure in both answers. So if you don't have in gallons, if you don't have minutes, you lose that point. This is worth 3 points. 1 point is for the units. 1 point is for the explanation. Now, when you see this, that should make you think of something. You should be like, oh man, that kind of looks like mean value theorem, doesn't it? You integrate something from 0 to b, smooth it out, divide by the base of the rectangle, gives you the height of the rectangle. That's what this is. This is mean value theorem. This is the average what? Average R. What is R? Average R is the rate of fuel consumption. Average rate of fuel consumption. They ask you to do it in terms of the problem, in terms of fuel consumption for the plane. So in the context of the problem, average rate of fuel consumption in, what are the units? Gallons. Now, this is going to give us gallons per minute times minutes, which gives you gallons. But then this right here is dividing by the base. That's divided by time. So it's going to give you units that, it's giving you average R. So what are the units of R? Gallons per minute from time t equals 0 to t equals b minutes. Like you got to put all those units in there. Okay. So, all right. So we got to start recognizing some of these kind of expressions that come up a lot and understanding how to interpret them, but they kind of, it's kind of similar a lot of times in different kind of contexts. So that's problem 3. It's kind of a interesting one. And so then we're going to go to problem 4. So problem 4, it says the graph of a differentiable function f on a closed interval -3 to 15 is shown in the graph above. The graph of f has horizontal tangent line at x equals 6, which it looks like it does, but you might go ahead and emphasize that because they told you. So this is some graph of f, and then look at this. Here's a new function, and g equals 5 plus the integral of the graph of f. Are you starting to recognize this? We did this on I think on one of the warm-ups or something. This is coming up where they give you a graph, and rarely they're just going to give you the graph and be like, oh, just, graph of the derivative is really popular, though. That's usually. So this is going to end up being the graph of g prime. We're going to show how that works out. So we don't have to think of that yet. We can say, well, what's G6? Well, G6 is plug 6 in to your function, and integrating any function from 6 to 6 or the same number to the same number, that's going to give you 0. So that's going to be 5. So that's G6. The point breakdown here is 3, 3, 2, and 1. So this is probably a point here. Now g prime of x is going to be the derivative of this. Now the derivative of 5 is 0, and then the derivative of the integral gives you, they undo each other and you plug the limits in, but then you got to multiply by the derivative of what you plugged in. It's a whole chain rule thing, right? Fundamental theorem of calculus part 2. That drops out, that drops out. So g prime of x equals f of x. This is a big deal for probably the rest of the problem. from this, we could say, well, g prime of 6 equals f of 6, which means we're looking for the y value on this graph. F of 6 is 3. So that's another point. Okay, now if g prime equals f, then g double prime is going to equal f prime, which means that g double prime of 6 equals f prime of 6 equals the slope at 6, which is the horizontal tangent, which is 0. Now, throughout this problem, this whole problem, parts A, B, C, and D, anytime you answer a question about G, you need to tie it to F because you have been given information about F, and you got to keep showing the relationship between G and F to support your work. Okay? So this is the graph of G prime, by the way, right? G prime equals F. So this is a derivative graph, and we know how to deal with derivative graphs. On what intervals is G decreasing? Now, G decreasing, anything decreasing, means that its derivative is negative. So we're looking for where it has a negative derivative. Now, remember, this is the graph of G prime. So it's negative here, decreasing, positive here, increasing, negative here, decreasing. Right? We've done that a lot. Here's a critical point, by the way. Probably need that for some other problem. Critical point. I mean, I could keep going. Relative, it's going down then up. So this is relative min. Up and down. This is relative max. We could start getting a concavity. I'm going to wait because I think that's on a future question. So we're going to say G is decreasing on -3 to 0 and 12 to 15. And usually we include endpoints for increasing, decreasing. And so that's a point, and that's a point, and then your justification is going to be a point. Justify your answer. Justify your answer. And don't say because this, like, you want to say, since g prime of x, which equals f of x, is negative for those intervals. -3 to 0, don't include 0 because it's actually 0 there, and 12 to 15. Now, it actually is negative at 15, -13 based off this graph, right? And the graph did include the endpoints. So that would be a good answer, stating where it's decreasing, stating why, because these corresponding intervals have negative g primes, but also keep reinforcing the idea of how you know g prime is negative from a graph that doesn't have anything about g originally. C. C says, on what intervals is the graph concave down? Well, we know from derivative graphs, the slope, this is going to be concave up, and this is going to be concave down, which means this is an inflection point, right? So, where's the concave down? And then justify your answer. Well, G is concave down on the interval 6 to 15, and we don't include endpoints. Now, why is it concave down? Since G double prime of x, which equals f prime of x, is negative, right? The slope of f is negative, which means G double prime is negative on the same interval 6 to 15. So that's 2 points. 1 point for the answer, 1 point for the justification. All right. So this is stuff that we've been doing, even since the end of last semester with these graphs of derivatives. But now we're having, in the work is kind of the same, but we're just having to really answer these questions and really explain ourselves. Now, D says, find the trapezoidal approximation for -3 to 15 of ft dt. So it looks like we're getting a break from G using 6 subintervals with delta t equals 3. I showed you guys that if you've looked at the 12.7b notes, I start using this delta a lot more. Delta means it's a Greek letter. It looks like a triangle. It's usually mean the represent the change in something. So it's kind of like dt, delta t. So we're using this picture. I think maybe I could pull it off. My picture isn't too messy. We're going from -3 all the way to 15. And we're doing 6 subintervals, 1, 2, 3, 4, 5, 6. And the delta is 3, which makes sense. They're all equal, right? And we're trying to do trapezoids. So when you do trapezoids instead of rectangles, you connect the endpoints and you find the area under those. Now, this is some weird stuff. Like there are clearly some trapezoids right here. You see that trapezoid, and you see that trapezoid, right? And then this one is like a triangle. Well, guess what? A triangle can be thought of as a trapezoid where one of the bases is 0. And here's another trapezoid, but it's a triangle and it's negative. So you got to count those ones as negative. We're not doing area. We're using area to help us find the values of these shapes, but if it's below the x-axis and you're integrating, that's all we're doing is just trying to integrate. It's going to come out negative. So we should show the work for that to show the trapezoids. I'm not going to draw a separate picture because I already kind of have this handy picture here. And the area of a trapezoid is the average of the bases times the height. It's really just like the area of a rectangle, base times height, but it has 2 bases. So you're like, well, what base should I use? Well, you average them because you get that base right exactly in the middle of them, which is called the median of a trapezoid, and actually is the base of the rectangle you would get if you kind of rearranged the parts of a trapezoid and made a rectangle out of them. So they really are rectangles. So this is an approximation. It's the average of the bases. Now the first one is -1 plus 0 divided by 2 times the height. The next one is 0 plus 1 divided by 2 times the height. The next one is 1 plus 3 divided by 2 times the height. The next one is 3 plus 1 divided by 2 times the height. The next one is 1 plus 0 divided by 2 times the height. And the last one is 0 plus -1 over 2 times the height. So you really want to show this work. You want to show them doing trapezoids. You might get points just for setting that up correctly. I would label it too. Don't just start throwing numbers here. Tell me, lead with what is all this going to be, and use appropriate symbols like this is an approximation. So now we just got to figure out what this is. There is something a little tricky here that you don't have to do, but you notice how they all have 3 halves because they all have the same height. They all have divided by 2 to get the average of the bases. So then we can say, well, this is -1, this is 1, this is 4, this is 4, this is 1, and this is -1. It's kind of slick. So then those are going to cancel. Those are going to cancel. We get 8, which is 4, which is 12. So that's our approximation with trapezoids. So we got a little break from B, and then you're not even asked to interpret it or justify it or anything like that. But you got to make sure you show the setups here. Anything you draw in your picture up here is not going to be getting you credit. So anything you draw up here is helping you figure out what the answers are. But then you need to make sure that work or the thoughts that you put in up here are reflected in what you put in your answer. Okay? So anyways, this is popular. They like to give the graph a derivative, and a lot of times they like to kind of like give it to you in disguise. Sometimes they'll just straight out, here's the graph of the derivative of some function, but this is f, and then they give us this g, and most of the questions were about g. And so we had to keep making those connections with that. Okay, last question. So I would say a lot of times they might give you a question where they just kind of have you do kind of function analysis. here's some functions, find some different things. And we were kind of doing that on the last problem. Like, hey, where's the concave up? Where's the concave down? Where's the relative max, relative min? This one has definitely a challenging question that could, that comes up here and there. And it's challenging more for free response because you have to show the work. The breakdown for points here is 2, 4, and 3. They give you a piecewise graph, piecewise function, which is not a surprise to us. We've dealt with that a lot this year. But then they say, is it continuous at x equals 3? Now, this is a question I asked you guys a lot first semester. I give you these piecewise, and usually the pieces themselves were continuous, but it was where they met each other that might not be continuous. And the way we would do it is we would say, oh, well, let's plug 3 into both of these and see if they both give you the same y values there, to see if that the two pieces, if they're connected, or if they're not connected. But that's not good enough for free response. You want to, that's a lazy way of doing it, which is great for multiple choice. But if you want to prove that something's continuous, you want to use what's called the definition of continuity. And so the definition of continuity, which we're going to use, and you don't need to write it down, but the definition of continuity says, this is what we're going to try and prove, that the limit as x approaches 3 of our function, which means that from both sides, because limits are two-sided, as we approach from both sides, that it actually equals the value of the function there. Because it's not enough for them to both agree, but then if you have an open dot or a jump, well, then it's not continuous. So we want both sides to agree, so they're connected, but we also want the value at that point to agree with what they are saying. This is what we need to prove that these are continuous at x equals 3. Now, what we need to do is we need to show that the limit as x approaches 3 from the left side agrees with the limit as x approaches 3 from the right side, because there's two different functions. So that's when we just plug it in and get the two y values and say, are they the same? That's what we're doing, but here's the technical way you need to do it. So this is what we're trying to do. So this is our next step. We're just trying to figure out what this side is. So now we're going to show the work for that. We're going to say, okay, well, the limit as x approaches 3 from the left side of f of x is going to be equal to the limit as x approaches 3 from the left side of square root of x plus 1, which gives you, now this isn't -3. You'd actually just plug 3 into it, and you get the square root of 4 is 2. And then we would do the right side limit. X as x approaches 3 from the right side of f of x, we get the limit as x approaches 3 from the right side of 5 minus x, and we get 2. And they're equal to each other. So this shows you that the limit as x approaches 3 overall exists, and it's 2. You guys remember that limits are two-sided, and the two sides have to agree for the overall limit to agree. So all that work right there was to get part of this right here. Now, the actual value of the function at 2 or at 3, if you plug it in, says we're supposed to use that one. We're supposed to use the first one, right? That one has the or equals to and 3. You're not supposed to. So we say, okay, well, that's the square root of 3 plus 1, which is the square root of 4, which is 2. And so now, now we can say, well, the limit as x approaches 3 of f of x must equal f of 3, which is the definition of continuity. So f is continuous at x equals 3 is our final answer. But we have to use the definition of continuity that says the limits agree with each other and agree with the value of the function there. They don't have to agree with the value of the function there for the limit to exist on its own, but for the graph to be all connected, no holes, no jumps, that has to be true. So we did a bit of work to find what the left side was. We did some work to find the right side, and we were able to show that they both equaled each other. And that's the work you would need to get full credit. Okay? So the one-sided limits, I think they give you 1 point for, and then 1 point for the final answer, but you had to have the other work in there to get that point. So that was kind of a new challenging problem. B says find the average value of f. Oh, average of f on 0 to 5. Okay, well, this is mean value theorem. Okay, so that means f average equals, now it's not a derivative, so we shouldn't use a derivative one, but we want to integrate the area under the curve between the endpoints, smooth it out, flatten it out. That flattened out height is the average height. We're going to use the area under the curve. It's going to be the area under the smooth curve, which is rectangle, divide by the base of the rectangle to get the height of the rectangle. This is mean value theorem. So that's our general setup. To accomplish this, we're going to have to break this up because we can't integrate both of these at the same time. We're going to have to do that chunk 0 to 3 with that one, and then 3 to 5 with that one. It's all going to give us one area. And we've done this on recent tests. So we need to integrate from 0 to 3 of the square root of x plus 1 dx, and then from 3 to 5 of the integral of 5 minus x dx. This is all important work to show. This is your setup, okay? In fact, this right here is worth 1 point. Show it. Now we just got to calculate it. We don't have a calculator, so we just have to go through it. It's 1/5 times the whole thing. You just want to do one average. You want to find one area divided by one base. Don't break these up and do them separately. Now, this is the same as 1/2 power. So this is going to be x plus 1 to the 3/2. Increase it by 1, divide by the new exponent. It does have an inner function, but chain rule, the derivative of the inside is just 1, so we don't have to do anything extra. You can do use substitution if you want. And then we're going to plug in the limits. Plus, this one's going to be 5x minus x squared over 2. And we're going to go 3 to 5. So we just got to get through this work. So this is going to be, if we plug 3 into this, it's going to be 4 to the 3/2 minus, now be careful when you plug 0 in, a lot of times it's 0, but here it's going to be 2/3 times 1 to the 3/2. Plus, here we're going to plug 5 in, we're going to get 25 minus 25/2 minus 15 minus 9/2. Now be careful, you have to distribute this subtraction or combine them together first. Now, I would do square root of 4 is 2, cubed is 8, so it's going to be 16/3 minus 2/3. This is a lot of work. This is going to be 50/2 minus 25/2 is 25/2 minus, we could give this least common denominator, it's going to be 30 minus 9 is going to be 21/2. So that's going to be 1/5 times 14/3 plus 4/2. We could give least common denominator. And so we get 28 minus 12 is 16 over 6, which we could reduce, and we finally get 8 over 15. That was a lot of work. 8 over 15. Actually, I made a mistake somewhere. So let me see. I'm not perfect, but let's see, where is my mistake? I think I'm good right here. 28. Am I doing it? 28 minus 12 is 16 over 6 is 8/3. 8 over 15. I mean, I don't know. Can't find the mistake. 28 minus 12 is 16 over 6, right? The other thing is we could have said, well, this is 2 and just 2 over 1, and then it'd be 14 minus 6 is 8/3, which is what I got. Oh, it's plus. 28 plus 12/3 is 46. 28/6 plus 12/6. I was subtracting for some reason in my head. So this is going to be 20 over 3. This is going to be 20 over 15, which if you really wanted to, you could write as 4 over 3. You don't have to simplify your answers on free response, so it might be a better idea to just leave things unsimplified. But that was just mean value theorem. I mean, gosh, it was kind of a lot of work after we set it up, but it was a little tricky to set up. C says, suppose that the function g, so here's a new piecewise function, where k and m are constants. If g is differentiable at x equals 3, what are the values of k and m? So this is actually a question I put on several tests. So we're not asking if they're continuous, we're trying to ask if they are differentiable, which means that the slopes have to agree on both sides. Now the graph has to be continuous, first of all. So we have to first prove that it's continuous, because just because the slopes agree, if it's not continuous, it doesn't matter. So I'm just rewriting this right here next to my work. Okay. So it has to be continuous. Now I'm going to go ahead and be lazy and not go through the technical definition of continuity. So continuous means that the y values agree with each other on both sides. They both approach the same thing. So if I plug, so they have to equal each other, right? In general, and we're talking specifically at x equals 3, right? So we're going to plug 3 in. And so that's going to be square root of 4. So this is going to be 2k equals 3m plus 2. This is one thing that has to be true. And there's 2 unknowns, so we need 2 different conditions. So then the other thing is, so you get 1 point for establishing this, and then the other thing is that the slopes have to be equal. So what I usually do is I take the derivative of it piecewise, and I say, okay, well, this is to the 1/2. Now remember the x is just a number, so it's going to be 1/2 k x plus 1 to the negative 1/2, and the derivative of this is just going to be m. And this is going to be from 0 to x to 3. And this is going to be from 3 to 5. Now, I'm not really sure if I should set it equal at 3, because that's where they meet. And if it doesn't, the derivative doesn't exist there. If it's not differentiable, then we can't include it on either of them. So the slopes have to be equal. So that means that k over 2 square root x plus 1 is a little nicer way of writing it, equals m. And so you get a point, I think, for writing that. Well, then we got to plug 3 in. And so that's going to give you k over 4 equals m. So now we have our system of equations. So you could try and find k, you can try and find m first. I mean, I think it's going to be easiest to say, well, let's put k equals 4m in for k, right? So we get 2 times parentheses 4m. I'm solving the system of equations using substitution. So we get 8m minus 3m equals 2. So 5m equals 2. So m equals 2/5. Now, did they ask for m? Oh, they asked for m and k. So that's m. We still need k. K equals 4 times m, which is going to give you 8/5 for the k value. I don't know if you guys remember doing problems like this on tests in my class, regular tests. So This is worth 3 points. 1 point for this, 1 point for this, and 1 point for your final answer being correct. So this problem kind of had a lot of algebra work, but there you go. I hope this will help you for your upcoming practice test, and I hope you tried all these first and then figured them out. And the level of stuff I'm showing here is the level of stuff you want to show in your work: organization, label, setups. If you want to get full credit on for your response, it's not just an issue about getting the right answer. It's usually the right answer is worth like a third of all the points, and the other 2/3 of the points are for the work and the setups that lead to it. So make sure you label things. Don't leave important ideas out. Write them down.